Hello everyone, welcome to another lecture of Microcontrollers with Lab. In this lecture, we are going to focus on sequential circuit analysis. These are the topics that will be covered in the first and second part of this lecture. And they include the state tables, state diagrams, equivalent states, and Moore and MIDI models. Alright, let's start by having a look at the block diagram for the sequential circuit first, as we already have seen. Here we have the general model, we have the combinational logic circuit here at the core, and we have the storage elements here. And we know that the storage element is exchanging data with the combinational logic part. The states, the current state indeed, is determined here, and the next state is what we get from the combinational circuit as the input to the storage elements. So the current state at time t is stored in an array of flip-flops. This is the assumption that we have for the sequential circuits that we are going to analyze. The next state at time t plus 1, so t plus 1 here means the next time instant. If we are using the clock, we may say that here we have t, here we have t plus 1, here we have t plus 2, and so on and so forth. And this 1 doesn't mean that it will be in 1 second or 1 minute or anything. So it just tells us the next rising edge of the clock, we can say. So the next state at time t plus 1 will be a Boolean function of the state and the inputs. As for the outputs at time t, they will be a Boolean function of state and sometimes of inputs. Okay, so it will determine whether the sequential circuit is of type Moore or MIDI. Let's go through an example. Here the block diagram for the sequential circuit is given. We have two D-type flip-flops, and there are a given number of the gates, AND gates, OR gates, and an inverter. We have one output Y, one input X, and two state variables A and B, which are the outputs from the D flip-flops. So input is X, output is Y, and state variables indeed are A and B. Okay, so they are not states themselves, but we have the, let me maybe correct it here, state variables. Let's see what will be the output function. For the output function, we need to look at Y, the expression that we have for it. We have the AND gate here, which receives two inputs. One comes from the output of the inverter here, and that one is connected to the X, which is the input. So we have Y at time t is equal to not X at time t, and we have an expression which is the OR of two terms. If you look at the terms or the inputs to the OR gate, one input is connected to the output of the second flip-flop, and the other one is connected to the output of the first flip-flop here. You can just follow it. So therefore, the expression for Y will be equal to not X and A at time t or B at time t. So we have it for the output. Y at t is equal to not X at t and A or B. This is the expression that we have for the output function. As for the next state functions, we need to determine the A. So here we have A at t, B at t. We need indeed to determine the input to the flip-flops. The input to the flip-flop over here will be considered as A at t plus 1, and the input to this will be considered as B at t plus 1. So we need to find out the input to the flip-flops. A at t plus 1 and B at t plus 1 could be obtained looking at the block diagram of the circuit over here. So A at t plus 1, or the input to the first flip-flop will be the OR of two terms, and those are the AND. The terms are in the form of AND of two variables. So for A, we will have X at T and A at T, or here we have X and B. X and B. Or we can alternatively write it in the form of X at T and A or B. So that's what we have for A, and then for B, for the input of the second flip-flop here, B at T plus 1, and we consider it as B at T plus 1 because this will determine the next value for B, or then the value which will be stored in the flip-flop at the next rising edge of the clock. And we can see that it is in the form of X at T, and so the second input comes from not A. So X and not A at T. We have the expression for A at T plus 1, B at T plus 1, and also the output or Y. And we can check them in the next slide, as you can see here. So for Y, we have not X and B or A. For B, we have not A and X. And for A at T plus 1, we have A and X or B and X. So you can see how the Boolean equations for the next state variables and for the output could be formed referring to the block diagram of the circuit. Here you can see the time diagram indeed, and we can see where in time are the inputs, outputs, and the states defined. We have several rows here. The first one is called the reset, and when we will see maybe later, once we receive the rising edge of the reset, the flip-flops will be reset to 0. Okay, and you can see that they are equal to 0 here for A and B. And then we have the clock input. You can see that it is in the form of a square waveform. In this circuit, the circuit is indeed sensitive to the rising edges of the clock. Okay, so these rising edges of the clock will be important. We need to have a look at them. And then we have the X, which is the input, and that's out of our control. Let's say someone is changing the value. For simulation, we may do it ourselves. And then we have next value for A, next value for B, and the current value for A and B, and finally the output. Something important here is that when you want to determine the value for A and B, you just look at the value just before the rising edge of the clock that we have for NA and NB. So for example, in the first case, T here, if you check the value that we have for NA and NB, you can see that here for NA we have 0, and for NB we have 1. Therefore, after the rising edge of the clock, the value for A will remain as 0, and the value of B will switch to 1. Then, in the next rising edge of the clock at T plus 1, we can see that for NA we have 0, and for NB we have 0, and therefore, after the rising edge of the clock, A and B will switch to 0, or they will remain at 0. And similarly for the next rising edges of the clock. Apart from A and B, which change their value after the rising edge of the clock, the others, like Y, X, and NA and B, which are the next values for A and B, could change their value at any time depending on whether the X has changed its value or not. Okay, but for A and B themselves, for the output of the flip-flops, they will be changed only after the rising edge of the clock. All right, so now we are going to see about the state table. State tables are kind of similar to the truth tables, and they could be used in order to help us to analyze the behavior of a sequential circuit or in order to design a sequential circuit. So basically, a state table is a multiple variable table with the following 4 sections. The first section is the present state. The next one is the input, and then we have the next state, and finally we have the output. The present state includes the values of the state variables for each allowed state. So the values of the state variables like A, B, C, and so on and so forth for each allowed state. The input will determine the input combinations allowed. We might have a single input or multiple inputs. Then we have the next state, which shows us the value of the state at time t+1 at the next rising edge of the clock, let's say, based on the present state and the input. And finally, we have the output, which will give us the value of the output as a function of the present state and sometimes the input. If we look at the state table in the form of a truth table, then we will have the input and present state forming the inputs for our truth table, and output and the next state will form us the outputs. So in the input side, we will have the input and present state, and here we will have the output and the next state. So in this case, we will have a kind of truth table, and looking at that truth table, we can find out expressions for output and next state, and as a result, we will be able to construct a sequential circuit. Okay, so let's go through an example. Here we have the same sequential circuit for which we have obtained the expressions for the next state variables and for the output referring to the circuit diagram. Now we are going to form a state table for the same circuit. If you look at the state table here, we have the present state and the input. For the present state, we have two state variables, A and B, and for the input, we have X. So indeed, if you look at this as a truth table, we have three variables, A, B, and X, and as a result, we should expect having 8 rows. And you can see that it's the case. Yeah? We have 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on and so forth until 1, 1, 1. And then we have on the output side, we have the next state and the output. As for the next state, we have two variables, A at t+1 and B at t+1, and for the output, we have Y at t. And to fill the table, we just refer to these equations that we have here. We just plug the values for each row and then obtain the value for the corresponding variable, A at t+1, B at t+1, and Y at t, and then fill the table. And I think you can easily do it for this example by referring to those equations. So in this case, we have the state table filled for this example. That's one way of forming the state table. We have an alternate state table as well. In this case, we keep indeed, or we push kind of the input towards the output and the next state indeed columns. So we will have a two-dimensional table in this case, which matches well to a K-map. So the present state rows and the state columns in gray code order will be used. We have the same expressions as before, but in this case, we have 4 rows in total because we have two state variables, A and B. Therefore, there will be 4 possible options. Then for the next state and for the output, since we have a single input, we will have to separate, let's say, sections for each. When x is equal to 0 and when x is equal to 1. When x is equal to 0, we have 2 columns here for A at t+1 and B at t+1. When x is equal to 1, similarly, we have it here. And then for the output, when x is equal to 0, we have 1 column, and when x is equal to 1, we have the other column. So sometimes this kind of state table, which is kind of more compact, could be more useful than the normal way of having the state table. So it will also depend on the application or on the example, on the circuit that you are going to analyze or design. Alright, so next thing regarding the sequential circuit analysis is the state diagram. The sequential circuit function can be represented in a graphical form as a state diagram, which has the following components. We have a circle, so this will be a circle that we may use to represent a given state. So there will be a state name. For each state we will have a circle showing that state, and we will have the name for the state usually written inside. So state, let me not use letter A, but state 1, okay? Then we may have another state as S2 and so on and so forth. So a circle will represent a state, and we need to determine the name of the state there. Then the next component is a directed arc from the present state to the next state for each state transition. We can refer to the state table, and then depending on the input usually, if we are currently at state 1 and as an example, we receive the single input that we have being equal to 1, then we will transit to state number 2. Okay, so this is the directed arc. Please pay attention to the direction. Okay, so the current state is S1, the next state is S2 when the input is equal to 1. Alternatively, we can have this case when x is equal to 0. If the current state is S1, the next state will be S1 as well. So we will remain at the same state. So again, this is a directed arc. I already have shown you, we will have a label on each directed arc with the input values. So like x equal to 0 here, which causes the state transition. And we will have a label either on each circle with the output value or on each directed arc with the output value produced. So let me show you here. If we assume that the output for this example depends only on the state, then the output will be shown in this way. For S1, if I assume that we have a single output, whenever we are in S1, the output will be equal to 0, and whenever we are in S2, the output will be equal to 1. In this case, you can see that the output doesn't matter on the input, so it depends only on the state, and we can show it inside the state. But as another example, we may have this case. S1, S2, and we have the directed arcs like here. Now we can say that if x is equal to 0, the output will be equal to 1 and we will remain at the same state. But if x is equal to 1, then the output will be equal to 0 and we will switch to the state number 2. For state number 2, if x is equal to 1, the output will be equal to 1 and we will remain there. But if x is equal to 0, the output will be equal to 0 and we switch to state number 1. So you see that depending on whether the output depends on the state only or it depends on the state and the input, we determine the output value on the directed arc or inside the state. So those are the main elements that we have for the state diagrams. Okay, so this is something that we already have discussed, but here we are learning about the type of the output. So if the output depends only on the state, we will show the output inside the circle. So, and there we will have the state slash output. And in this case, we say that the output is, or the sequential circuit is of type Moore indeed. Okay. So we have the Moore type when the output depends only on the state. On the other hand, if the output depends on state and the input, then the value of the output will be shown on the directed arc in this format, input slash output, and that's something that we already have seen. And in this case, we have the mealy type circuit, sequential circuit, or the state, yeah, because we may have a combination of these kind of states in a single circuit. So it's better to call them mealy type state or Moore type state. So for the mealy again, for the mealy again, we have the output depending on the state and input, and for the Moore, it depends only on the state. Here we have the state diagram for the same example that we had. As we had A and B as for the state variables, it means that we will have 4 states in total. And for those 4 states, we are using 4 circles. Referring to the value that we have for A and B, the state variables, the states are shown here. So instead of S1, S2, S3, and S0, we just directly have written the values for the state variables: 0, 0, 0, 1, 1, 0, and 1, 1. So those are the names that we have assigned to our states. And then you can see that for the state 0, 0, if the input is equal to 0, output will be equal to 0, and we will remain at the same state. But if input is equal to 1, the output will be equal to 0 again, and we will switch to the next state, which is 0, 1. In state 0, 1, if input is equal to 1, output will be equal to 0, and we will switch to 1, 1. If input is equal to 0, output will be equal to 1, and then we will switch to the state 0, 0. And you can see it for the other states, state 1, 0, and 1, 1 as well. Generally, in this sequential circuit, in this state diagram, you can see that the output depends both on the input. Output is a function of the inputs and states. So not only the state, and you can see which type it is. It is of type mealy. But if you pay extra attention here, you can see that for state number 0, 0, for state 0, 0 indeed, the output is always equal to 0. So we can see that for that case, for the state 0, 0, the output depends only on the state, and as a result, we can show it here. So I can rewrite it in the form of 0, 0 slash 0. It means that for this state, we always have the output equal to 0, but that's the case only for this state. For the other 3 states, it's not the case. So if we have a large circuit, let's say the diagram may become confusing and not that useful, but for small circuits, it's an easier way to analyze or to start to design a sequential circuit. Another thing that I would like to mention here is that some of the states in this example could be considered as equivalent of each other. So let's see it in details. If I consider the state 0, 1 and 1, 1, so these two, you can see that when the input to each of these states is equal to 0, so these two cases, when the input is equal to 0, the output is equal to 1, and the next state is 0, 0. So for both cases, if x is equal to 0, y will be equal to 1, and next state will be 0, 0. On the other hand, if x is equal to 1, and we can check it for both, if x is equal to 1, the output is equal to 0. If x is equal to 1, the output is equal to 0. Okay, but the next state in this case will be different. So next state next state will be 1, 1, and the next state here will be equal to 1, 0. But if we consider the 1, 0 state as well here, we can see that for that 1, 0 state, when x is equal to 0, y will be equal to 1, and the next state will be also equal to 0, 0. And that's shown here. And on the other hand, if x is equal to 1, y will be equal to 0, and the state will be 1, 0. Okay. Now, having this in mind, having all this in mind, we can assume that it's possible to combine these three states and obtain a single state. So 0, 1, 1, 1, and 1, 0 could be considered as state S1, I call it. When x is equal to 0, y will be equal to 1, and the next state will be 0, 0. And then when x is equal to 1, y will be equal to 0, and the next state will be S1 itself, because we will remain here. Okay. So in that sense, we can simplify this state diagram into this. We will have 0, 0 with 0 as the output, and we have, I called it S1. If x is equal to 0, y will be equal to 1, and we will transfer to 0, 0. If x is equal to 1, y will be equal to 0, and we will remain in S1. For 0, 0, we already have seen it. If x is equal to 0, y will be equal to 0. And if x is equal to 1, which is this case, we will transfer we will transit to the S1 case. So x equal to 1, y will be equal to, y is still equal to 0, so there's no need to show it here and there. So with x equal to 0, we remain there. With x equal to 1, we will switch to S1. And in this way, this kind of same circuit could be indeed implemented in a simpler way. All right. The next topic that we are going to talk is about the Moore and Mealy models, as already we introduced them. For the sequential circuits or sequential machines, we also use the finite state machines term as well. So FSM is also frequently used. And we have two formal models for that, the Mealy model and the Moore model. As for the Moore model, we know that the outputs are a function of states only. And for the Mealy one, the outputs are a function of inputs and the states. So for the Moore model, since the outputs are a function of only states, usually they are specified on the states, and here for the Mealy model, they will be usually specified on the transition arcs. Sometimes this kind of specifying whether a state diagram is Mealy or Moore makes the design and analysis simpler. Here you can see the Mealy and Moore state diagram examples. We have the Mealy model here. In the Mealy model, the outputs are a function of inputs and states. So y equal to 0 is here, and y is equal to 0 here, depending on the states that we are and the inputs that we have. Alternatively, we can combine them into the Moore case here. And in the second case, when we are in state number 1, if x is equal to 1, y is equal to 1. When x is equal to 0, y is equal to 0. So in general, for this case, the outputs depend on the states and on the inputs. In the second case here, we have the Moore model, and the outputs are the function of the states only. So they are shown here. When we are in this state, the output is equal to 0. In this state, output is equal to 0. And in this state, output is equal to 1. So you can differentiate the Moore and Mealy models from each other in this way. For the Mealy and Moore models, the state tables could be also kind of different. For the Moore model, the output will be only a function of the state, so we don't have the inputs listed here. But for the Mealy one, the output will be a function of the input as well, so we have the input shown in the table as well. And as I maybe mentioned earlier, we can have a mixed Moore and Mealy outputs depending on the case. This is what we have, I think, from the previous example. You can see that in the state 0, 0, the output is always equal to 0, independent of the input. But for the other states, the output depends on the input and the state. And you can see that they are shown here on the directed arc. So we can have a combination of the Mealy and Moore type outputs as well. Alright, so I think that's all for this part of the lecture. In the next part, we are going to go through another example of analyzing a sequential circuit. Thank you for watching and see you in the next part of the video lecture soon.